All right. Hi, everyone. It's great to virtually be here. It's wonderful to be able to talk at this workshop. I'm going to talk today about some of our work that I'm calling Beyond Provable Robustness. This is going to be work that kind of spans both talking about some of the stuff we've done in provable robustness, which I'll talk about what that means in the context of adversarial robustness, as well as sort of what I think the next steps are for the field, and sort of from this perspective of sort of machine learning robustness, what do I think is really going on here? I should start out by saying that this work is largely due to a lot of wonderful collaborators. So here I have my students, and this is also collaboration with a few other people as well. But here I'm showing my students and a few other actually student collaborators. So the students have their pictures here. All right, so just to kind of dive right in, this talk is going to be about kind of traditional notions of adversarial robustness in machine learning. So I'm going to start off by first giving a little bit of background on that. This is a very broad workshop that I'm speaking at here. And so many of the talks are going to go quite far beyond or capture notions of robustness and trustworthiness that are well beyond what I'm talking about here. What I'm going to talk about in this talk is largely kind of a very restricted notion of robustness that comes from adversarial robustness. It's an area that I've worked in a lot, and a lot of other people have worked in this field as well. But I do want to preface everything by saying this is, of course, a very narrow field and a very narrow definition of what we mean by robustness. And so hopefully by the end of the talk, I can actually also do some a little bit broader discussion, and certainly the panel later, do some broader discussion about where we might go from here to get beyond these sort of simple notions of robustness. So I'm going to start with some basic background on adversarial attacks, what these things are in the context of deep learning systems. And then I'm going to talk about a lot of the work that we've done on provable robustness. So this is actually how we can build machine learning systems that are provably unable to be attacked in this way, at least to a certain extent. But then I actually want to sort of go beyond that, and that's the title of this talk, I know, kind of going beyond provable robustness, because I also want to talk about what we can do, or what some of our current work is, that thinks about ways to either get beyond that, or thinking about issues that go beyond just provable or certified robustness, because I think that this is one piece of the puzzle, but it's only a small piece, and I'll sort of mention some of the work that's ongoing in this area. And then I'll finally finish with one slide on kind of my hopes for what's next in the field. It's a field I've been working in for some time now, and I have some sort of strong opinions about what I think is maybe good or bad directions for where we go from here, and I hope I can provide a little bit of motivation or insight into where I think we might want to go from here. All right, so let's start off though with a background on adversarial attacks. So I'm sure most people at this workshop have seen these kind of pictures before. They're sort of classic in machine learning these days. This is a figure from Alexander Madri's group, but the same thing actually has occurred the same picture occurs in its basic form in many different settings. The idea here is that machine learning systems, despite how well they work, are fundamentally, I would argue, broken in a very foundational way. And the idea here is that you can take this image over here, like you have a pig, like you have in this image on the left here, and you add a little teeny bit of noise to that. And to be clear, this is a small multiple of this noise. So it's the resulting image you get is the image on the right, and it's undistinguishable from a normal pig. But yet a deep learning system will with very high confidence classify that as an airplane. And the idea here, the way this is working is that this is not random noise that's being added to the image. What's actually happening is that we're solving an optimization problem to construct this noise. So in particular, we're maximizing over some perturbation, which we call delta here, within some set that we're calling uppercase delta. And both those are going to be very important actually throughout the rest of this presentation. Little delta we call the perturbation, and big delta we call the threat model. And so we're trying to find the perturbation within the threat model. In this case, this threat model actually involves essentially very low magnitude perturbations you can't even see. And under this class of potential perturbations, we select the one that maximizes the loss, or in this case, actually minimizes the loss on some different class, like an airliner class, as well as maximizing the loss in the original class of pig. And this is sort of a very visceral example here, because the image on the right looks exactly the same to all of us. In fact, it is exactly the same image. We can barely even see the difference here, right? And so if these machine learning systems that we are putting all our trust in can't even figure this out, then it seems like we're making some fundamental mistake here. And there's been a lot of interest in this work in recent years, though I should also clarify that this work actually goes, there's work that dates back much prior to sort of recent work in the area, and actually the work has been going on for a very long time in this sort of notion of attacking and adversarially attacking machine learning systems. So after I sort of present this, I actually want to answer another question, which is why should we care? Which is sort of a funny question to ask because it seems so obvious this is a problem. But really, I would argue you actually should ask this question about why we should care, because it's not clear that we should care. Because you probably, by all accounts, don't have an adversary that's trying to change your inputs at the pixel level. Or if you do, you have bigger problems, right? Than someone accidentally changing your pig to be an airplane. You've already been completely breached, and nothing else is going to matter. So it doesn't really matter if you can trust your machine learning or not. I would argue there are actually two really important reasons why we want to think about these adversarial examples, despite this fact that probably these exact settings are not that realistic. The first is that there are genuine security implications. So these things are not just virtual; they actually also can transfer to physical world attacks. And I think actually I won't bother talking about this too much because I believe that the next speaker actually is the person in this first photograph here. So it's my colleague at Carnegie Mellon, Leo Bauer, and he's going to actually I think talk about this a little bit more. So we've also done some work, for example, in image, this one on the right here, in object detection, trying to put patches and images to make everything else in the scene disappear. But I would say that even ignoring the security implications, which I actually am going to do for the most part, and this is not the main motivation for me, though it's a large motivation, I would also argue that this says that these examples, they say something very fundamental about the nature of deep learning, about what it is we're learning in these classifiers, and what really these decisions that these things make really look like. Because however they're working, they're not working like humans are, right? Because we know it's a pig, not an airplane. And so this says something very fundamental about the nature of what deep classifiers are doing, I think. And so because of this, it's sort of a natural goal to try to design systems that are not going to be susceptible to these attacks. In other words, can we make a classifier that actually will classify this thing on the right as a pig, despite the fact that it's been adversarially perturbed? And the short answer is yes, we can do this to a limited degree of success, and this is actually what the first part of this talk is going to be about. The simple idea here is that instead of minimizing, most machine learning systems are trained basically to minimize the expected loss of our actual data points, right? But what this adversarially robust setting is actually considering is something very different. It's actually considering evaluating your system based upon the worst case loss in this perturbation region. So you're now perturbing your example as we did before, and you're actually evaluating, with some perturbation in some set, and you're actually going to evaluate the power of this classifier under that worst case performance. And so if you're going to do this, you better train your system not based upon the first objective, not based upon this one here, which is what most machine learning does, but actually based upon the thing you really care about, which is the robust objective. Now, I actually want to pause for a moment and say, everyone sort of objecting that we don't really care about this, this objective of very limited or very specific perturbation classes here. I completely agree, and actually a lot of our current and ongoing work is precisely about how we can do things like come up with more realistic models for the threat model. I'll probably talk about that later, though. For now, I'll talk about relatively simple models. In particular, I'll talk largely about this threat model being what are called LP balls. So you basically can perturb your image within some norm-limited with some norm-limited perturbation. Now, there are really two ways people go about doing this. Or I should say two good ways. So the first way people do it is they just try something random, hope it works, and then a few weeks later, some other researchers have broken that defense and it doesn't really work at all. So there's two actual strategies which have sort of stood the test of time against these things. And they basically boil down to sort of an empirical approach and a more certified or provable approach. So the first approach that people use is adversarial training. So this actually goes back to some work by Ian Goodfellow, Alex Karakin, and Alexander Madry. And this basically, the idea is very simple here. It's that you sort of take gradient descent steps, not at your original examples, but at these worst case perturbed examples, and keep trying to play this game of, adding the worst perturbed example into your data set and playing this game. And this actually works well empirically, but somehow it's unsatisfying because oftentimes you can't really know this is going to work. Though we actually will return to this later on because it has actually stood up quite well under a lot of evaluation. The second approach, though, which is one that I am going to spend more time focusing on, are what are called certified or provable defenses. So there's been a lot of work in this area, including by a lot of my group and others. And the idea here is we actually want to get some guaranteed bound essentially on the nature of this objective. So if we can somehow, despite the fact these are complex functions, complex nonlinear classifiers, if we could actually somehow bound the performance of our loss, then we might be able to get an actual bound here. So this is actually what we're going to do, and I'm going to show you at least a few highlights of the ways we do that, because there really are two approaches we've taken to achieving these certified and provable defenses. The two approaches, which I'll talk about in a lot more detail, essentially boil down to convex relaxations and randomized smoothing. And these form right now, I think, the two most commonly used provable defenses against these adversarial attacks. Okay, so to get started now, let me talk a little bit about provable robustness. How do we actually attain these models that can give us guaranteed bounds? And the idea here is actually a fairly simple one. So the problem with deep networks, the reason why deep networks have these problems is that you can take a relatively simple image here, like the one on the right. So you can take a relatively simple examples here, like these X's and O's, and consider some sort of region around these things. So that's the nice, in this case, square boxes around them. The problem is when you feed them through a deep network, what comes out the other side are these very irregularly shaped, hard to reason about combinatorially complex objects owing to the nonlinear nature of the deep network. And this poses a problem for sort of even sometimes understanding, is there an adversarial example or not? And so the idea behind our first approach, this convex relaxation approach, is we're actually going to form convex tractable outer bounds over these regions, which we call the adversarial polytope, and we're going to perform robust optimization over this region. And so, in particular, this first approach is going to apply to networks with ReLU nonlinearities, though it can be generalized to more general activations as well. So how do we do this? I'm going to give a quick overview. That the math here is a little bit, well, math for both parts actually a little bit involved. But for a quick version, here's the following picture to have in mind. So the problem here is that these regions, these networks, are fundamentally nonlinear. And so they're nonlinear because they have these activation functions, these nonlinear activations like a ReLU or like a sigmoid or things like this. And so the idea is if we want to get an outer bound on the quality of these predictions, what we can actually do, or the size of these predictions, what we can actually do is form an outer bound, a relaxation on these nonlinearities. So for example, for the ReLU, if I were to know for maybe a lower and upper bound on how far we could span in the pre-activation space for that ReLU, so that's denoted here by L and by U, then I actually can form the convex relaxation of this ReLU, which looks like a little triangle here. And we know that the worst case perturbation under our original model here is actually going to be upper bounded by the worst case perturbation over this relaxed objective, because this thing here is a strict superset of the allowable activations here. And now similarly, this actually turns out to be hard to precisely optimize this thing. So we actually go one more step, and we actually form one more relaxation, which takes the dual of this problem here. It turns out this problem here, with just this relaxation, is now a linear program. So it's actually tractable because all the constraints are now linear. It's still too slow to solve, though, and so we end up forming a dual of this linear program and looking at a specific solution to this dual. And the details are actually a little bit involved. But basically what comes down to in the end is we get a fairly tractable way to form a closed form estimate of a provable upper bound on this worst case loss objective. All right, so that's the basic sort of technical idea of the approach here. And now, how does this work? It works pretty well in practice. So, for instance, if you take a data set like MNIST, well, I should qualify that. It works pretty well some of the time on smaller problems. So maybe I shouldn't say it works well in practice. It works pretty well on some small problems. So you can take a problem like MNIST here. If you train a normal network on MNIST, it gets pretty good error, right? It gets around the order of 1% error. But both the bound and the actual robustness here is basically 100%. So even with a really small perturbation size, this is the perturbation of epsilon being just 0.1. So the images are scaled between 0 and 1. I can perturb each pixel by a value of 0.1. And even with this sort of very small amount of perturbation allowed, you can basically completely fool you can basically completely fool the standard trained network here. This is actually showing the bound, not the actual amount, but basically the bound and the actual amount here are more or less the same thing. If you train a robust linear classifier, this has actually been very well understood for a while. So these are things actually very related to things like SVMs. You can do a little bit better here. So you can actually now get an actual guaranteed robust bound of 17%, but you pay a very big cost in accuracy. You've reduced your clean accuracy, but A, your robust accuracy is not that good, and B, your clean accuracy is reduced from 1% to 17%, which is pretty poor performance on MNIST. And then finally, with our method, though, you're actually able to maintain that same level of clean performance while being able to guarantee that no matter how many papers are written after the fact, right? No matter how many papers some certain researchers want to try to write to break other defenses, this will never be broken. So no classifier will ever, or no attack under this threat model here. So no attack. With this epsilon here, will ever attain more than 3.7% error here. And this bound has been improved since then by follow-on work. This work goes back to our original ICML paper in 2018. Now, the problem here, though, is that you can ask, well, MNIST is pretty small, right? Aren't we beyond that these days in deep learning? And of course, yes. But the problem here is that these methods, as like a lot of actually robust training, they scale poorly. So everything looks great on the MNIST size. What I'm showing here in the different colors now are different size networks. So you can train a small MNIST network or a larger one. You can also train a ResNet. We didn't bother on MNIST, but you can train ResNets too. And you can get pretty good performance here, robust performance. But when you start going to domains like CFAR, your accuracy falls off quite quickly. So this is showing now results for these different models with a allowable perturbation on CFAR of 2 out of 255 color values, right? So you're only allowed to perturb each pixel by 2 of its color values. Yet, this takes CFAR from its accuracy we're used to of 6 or 5% error all the way up now into the mid 40s when you're talking about certified robustness. And I should mention, I'm not showing it here, but you actually pay a very high cost. I'll show it in some other slides. You pay a very high cost in clean performance too. So these things also get on the order of 20% or sometimes 30% clean error as well. So we've suffered horribly both in terms of getting a certified bound and robust performance, as well as getting sort of clean label performance on our function on our underlying data set. So this is sort of a sad story for scaling, maybe. This led us into another set of techniques, which is sort of think about a different way of getting a certified defense using a technique called randomized smoothing. So the intuition here, just like I gave this intuition before about kind of outer bounding this polytope of reachable points, the intuition of randomized smoothing I think is a little different. The idea is that in some sense, if you have some query point here, which is the correct class, the correct blue class maybe, and there's an adversarial example, what that kind of means is that the adversarial examples are sort of these these regions that kind of jut into kind of these spikes that kind of stick into our decision space really close to the target point. In other words, it sort of says something very fundamental about the smoothness or lack thereof of our classifiers. And so one obvious way to fix this, which actually has been considered by others before us, we were just did some slightly different analysis on this, but it's also been considered by others before us. So LeCouillier et al. And Lee et al. Thought about this as well. The idea is actually quite simple. To avoid this, you can just basically apply Gaussian smoothing to the function. So you take your underlying classifier, which is this, signified by this sort of jagged region here, and I sample our original point or points around that point of our Gaussian, and I take them the majority sort of vote of all those points as my prediction. So I don't classify it according to just the single classifier. I now take a sort of a vote of many randomized classifiers and take their sort of joint average prediction. And this has the effect of kind of smoothing these boundaries. So the spikes that used to be there don't occur anymore. And in fact, there's something very sort of very specific you can say about this. So it turns out that this may seem surprising because the smooth classifiers, in the end, you're just doing sort of random Gaussian sampling that isn't not that you're not drawing that many samples here. But you can say that if the underlying smooth classifier correctly predicts the label, so what I mean by that is after you sample Gaussians and take their average, if that average is the correct class with probability p, then it turns out you can actually say that this classifier at this point is also robust with some L2 radius, so in a perturbation region, in this case an L2 ball, not an L infinity ball, but it's sort of more or less very similar in a lot of ways, which basically scales like the variance of your randomized sampling times the inverse CDF of a Gaussian. So this is a very sort of simple formula here that actually can give you certified results. But most importantly, this method actually does scale to much larger domains. So it scales in particular to things like ImageNet, and you can get ImageNets, you can train ImageNet size classifiers that actually give you provable robustness. And this is one of the first times, or this technique really is the first one. This class of techniques, ours and other people's works, was the first sort of class of techniques that were able to get this certified robustness at the scale of ImageNet. And so in particular, if you can take some of these, this plot here is a little bit more of an involved version than the last ones I showed you. But what this shows actually certified accuracy on the y-axis versus the radius of certification. So basically, if I consider a larger, this is basically your perturbation radius here. So the more you can perturb your examples, the of course less guaranteed performance you can have. But for example, if we look at maybe say this spot right here. Then this corresponds to what I'm saying here. So this is saying that on ImageNet I can perturb my my image with an L2 amount within an L2 ball of radius 1. Because it's a very small amount of perturbation, right? That sort of would be perturbing 1 pixel the whole amount, or perturbing a bunch of them a little bit less. But we can actually guarantee now a top one accuracy of 37%. So definitely not blowing away any records on ImageNet, but it's the sort of some of the first times that sort of these non-trivial guarantees on ImageNet have been possible. And also, of course, these results have been improved a lot upon since we published them. Okay, so with that all being said, I want to sort of give some sort of key takeaways or obstacles. I mean, they're more like obstacles in this approach here. Because I think people often sort of see these results and they say, oh, well, maybe robustness is solved. We've done it. We've solved robustness. And this is very far from the truth here. So this problem is still really hard. And the way I want to emphasize that is we are certifying relatively tiny regions in our images compared to what humans can easily do, right? So if you look back here, we're talking about 1 pixel total on these images in ImageNet, or maybe, 2 out of 255 pixel values on CFAR for the L infinity ball. These are tiny, tiny perturbations compared to what is easy for humans. And they don't signify anything yet compared to the robustness that we as humans have on these things, and that we really want to have on these sort of images. The second sort of key takeaway is that there's when you train these robust models, and this actually holds true for the certified ones I mentioned here, but also for the empirical ones, when you train them, you actually get much worse, not only sort of maybe not that great robust performance, that also degrades your clean accuracy a lot. So essentially, making these models robust enforces them to be smooth in a way that actually seems to drastically reduce the effectiveness of modern deep classifiers. And this is a big problem here. And finally, I also now want to finally sort of get at this underlying point here, which is this LP norm threat model. So the idea that somehow perturbations can or should lie within LP norms, this is really much more of a simplifying assumption, or a sort of a toy domain that we talk about, at least initially, because we can't even solve it. Even that's hard. But of course, any real threat model for any sort of real adversary or real security setting, this is both far too strong in some sense, because most adversaries wouldn't have complete that level of control, but it's also far, far too weak, because it doesn't capture nearly what a real adversary would do. A real adversary would not be confined to tiny imperceptible perturbations of your image. And so this problem, I really do believe, is actually still quite useful, but it's important to also understand the limitations of the problem. And I'll get back to this in a second later in the talk too, in my final wrap-up slides, because these are simple domains which tell us a lot about the nature of deep learning, but they are not realistic security scenarios. Okay, so with that being said, let me talk about some of our sort of current and ongoing work, which is going to be sort of a quick pass of some of our current work, which tries to go actually beyond some of these ideas of provable robustness to extend either classical empirically robust training or to extend the notion of what we mean by robustness, for example, by considering other threat models besides the LP ball. So I'm going to go through a few of these now. It's going to be quite quick, actually. But I also want to highlight some of the ongoing work in this space. So for example, one of the works we've been doing is about exactly this topic I mentioned to you before on alternative threat models. So a question that sort of comes up a lot is, why on earth should we think about these LP perturbation balls as being the right metric for understanding how an attacker could function? Doesn't really seem like a reasonable way of doing things. And it's definitely not. And so in some of our prior work, which was at ICML last year, we thought about a simple alternative model based upon a Wasserstein distance in image space. So instead of thinking about sort of images as just these things that you perturb, you think about actually kind of moving the mass of an image or shifting the mass of an image in a kind of an optimal transport setting. And so this actually can capture things like rotations or translations or distortions much better than traditional LP norms. Because, for example, if I take my original image here and I were to translate this thing over a little bit, so if I translate my image over a little bit, then under a L infinity norm, this is a huge difference because a few pixels are perturbed a huge amount. But of course, this is the same image. It's just translated over a little bit. And Wasserstein distance can actually capture things like this pretty well, or it gets at these things in a much better way than normal perturbation. Or normal sort of additive perturbation models do. Again, just being very sort of high level here, the actual challenge of this is actually coming up with an efficient way of projecting onto the Wasserstein ball the set of all examples that have distance less than some amount, but we developed an efficient way of doing that. And then we can actually see that when you apply these perturbations to things like CFAR images, they end up changing the image, not just like with this random noise, but they actually end up changing it at the boundaries of this image here. So you actually have these sort of, the biggest changes occur kind of at the boundaries, suggesting it's kind of attacking more of the semantic properties of the image. Though to be clear, we're still very far away from sort of real semantic notions here. So that's one bit of work we've done in sort of building upon these notions of provable robustness, or trying to sort of understand them better. Another work we've done is on sort of actually going back to the empirical side of adversarial training. We've thought about ways to make this process much faster. I actually want to highlight this specifically because this paper appears here at ICLR in a few days, so I should have gotten the actual time. But anyway, this is the name of the paper. It's called Fast is Better Than Free, Adversarial Training Revisited, and just to sort of highlight going after that. You might want to check it out in the ICLR sessions if it sounds interesting. But the basic idea here is that when it comes to adversarial training, there are a few problems. So not only, so adversarial training is this other approach I mentioned before, which basically involves running an optimization method like predicted gradient descent to find the worst case perturbation, and then training against that worst case perturbation instead of the nominal examples of your class of your data set. Now, this is not the first method. So before PGD was sort of became used popularly for adversarial training, even simpler methods like the fast gradient sign method, which is to sort of actually take a single gradient step to find the worst case example, were actually these other alternative methods were actually much more common, and they're much faster. But however, methods like the fast gradient sign method, which was used sort of for a while before, these were actually sort of dismissed kind of early on, because it turns out that models trained by them were actually very vulnerable to more fine-grained attacks. And so the field kind of abandoned even thinking about using FGSM training for adversarial robustness. But it turns out, as we show in this ICLR paper, and this is actually, and I'm just saying this now, this is actually very surprising, so it's been quite thoroughly vetted by a lot of people since then, but it turns out that actually you can kind of do some simple fixes to make single-step adversarial training actually work just fine. And so basically it involves, instead of always starting at your example, you actually first randomize a little bit and then you take a step. And it turns out when you do this, at least compared to the reported results, these are our FGSM methods basically basically perform as well as sort of the reported results for PGD training. So again, on something like CFAR, we achieve very similar levels of performance here in terms of the clean error, and more importantly, in terms of the robust error, we get sort of very similar performance between our method in the orange here and kind of classical PGD training in the blue. But of course, the real benefit here is that the fast gradient, the fast adversarial training takes vastly less time to train. So we can reduce, in particular, this original model here, this original adversarially robust CFAR 10 model took 84 hours of time to train on a GPU, whereas with this much faster method and some other tricks like half precision and stuff like that, though this doesn't apply, even with all these tricks, you cannot even come close to bringing down adversarial training to this fast. But with all these tricks, we can train a CFAR model in about 6 minutes, which is a huge advance upon what sort of is currently done. And even on a bigger data set like ImageNet, we can now sort of feasibly train much larger ImageNet models in a reasonable amount of time, like 12 hours. But actually, all hope is not lost for PGD yet, because there's actually something interesting about. So the results I'm showing here were actually from the reported results on Alexander Madri's paper talking about PGD-based training. But actually, in another paper another preprint we have available right now, we also actually look more closely at the performance of adversarial training and notice something sort of very striking in adversarial robustness, which doesn't happen in deep learning. So it turns out that in adversarial robustness, there's a much bigger problem that arises when it comes to overfitting. So in standard deep learning, you kind of don't worry about overfitting, right? You train your algorithm for as many epochs as you want. You don't think about early stopping because we have enough regularization methods that have sort of fixed this thing, and we sort of know how to make you keep getting your training error lower and lower, and your test error just keeps improving, or at least it plateaus and doesn't get any worse. It turns out the situation in robust training is very different, and this is actually, again, largely interesting just from a standpoint of our understanding of deep learning. So if you actually looked at that training that they did for PGD-based training, they trained for 200 epochs. But the final accuracy, which is the one here, maybe I'll choose a different color. The final accuracy, which is the one here, is actually, or final error, is actually about 8 points higher than the actual test error was right after they sort of dropped, did the first first learning rate decay after training. And the interesting thing here is not, so what it actually means is that PGD, if you do it correctly and sort of do early stopping properly, you can actually achieve state-of-the-art results. And in fact, this is maybe a sad negative result, but despite extensive tuning, we found that really no more recent method, so all the advances people have sort of been making on tweaks of adversarial training since the PGD sort of basic, the sort of PGD methods, basically work worse than just PGD with good early stopping here. And in fact, there's a recent leaderboard that some people maintain, evaluating these methods against very sort of sophisticated attacks, and we are here, which is the best performing method that does not use additional data. So we just use the CFAR data set. These other ones use all augmented data, not just with simple augmentations, but with actually new data, period. And without doing that, we're able to actually get, of the methods that don't do that, we actually have the best performance with simple PGD and early stopping. And maybe even more interesting in this paper is that we also tried every other single regularization technique that's used in deep learning that people try these days. So, drop out and cut out and all these sorts of things, and nothing actually solved this problem. So we fundamentally don't understand the nature of overfitting in adversarially robust deep learning, and it's of a very different character than traditional deep learning. And finally, almost everything I've talked about here deals with sort of providing or defending classifiers that you can train yourself, right? So both the robust classifiers require that we actually train the classifier against this robust objective, or require that we train in an adversarial fashion to get our with this adversarial empirical to make empirically robust models. We need to use this adversarial training mechanism, which is also requires that we be able to train our model from scratch. So we also know that sort of standard off-the-shelf models, for the most part, are not robust at all. And this raises sort of an interesting question: is can we somehow make these models, existing models, pre-trained models, robust? And it turns out we can. So some recent work, which I'm also going to highlight, this is work in collaboration with Hadi Salman and some colleagues at Microsoft Research. It turns out that by taking our sort of normal image here and by applying randomized smoothing, so adding this Gaussian noise to it, but then most classifiers are really bad at Gaussian, with Gaussian. Pre-trained classifiers cannot classify Gaussian perturbed examples. So we actually also add to this, before we classify them, a custom-trained decoder. So a custom-trained denoiser. And so we denoise, we add noise, and then we denoise so that we can have this whole end-to-end smoothing, randomized smoothing process still apply here. And by doing this, we actually can certify, sort of for the first time, black box classifiers that no one has actually trained to be robust. And we demonstrate this actually, again, that the details of these curves aren't too important. They're actually not meant to be visible. But the actual parts which you hopefully can see is the sort of headers here, where we actually go ahead and create, without of course having access to any of the code or data here, we create robust versions of publicly available image classification APIs like the Azure API or the Google Cloud Vision API and others. Okay. So with that all being said, I want to take the little time I have left to sort of discuss what I hope can be next for the field. I think we're making a lot of progress in this area, both on the certified robustness side, and we can say some sort of pretty impressive things that were, 2 years ago were not thought to be possible. We now can say some pretty impressive things about the nature of guarantees we can make about the nature of classifiers under these attacks. And we also understand and know a lot more about sort of practical empirical robustness and making these things robust in practice. And so the question that I sort of think about a lot now is what's next for the field? I mean, the first point I want to make, of course, which I should highlight before saying anything else, is that it's not like we've solved this problem. So we haven't actually solved this underlying problem here, and there is a lot more progress that can be made even in these very limited settings that we're talking about so far. So I think even under these very restrictive LP norm perturbation models, there clearly is still massive room for improvement, right? We're nowhere close to the performance that we would expect, that we're used to in standard deep learning systems. And so the question is, why is this gap still there? Why is this gap seeming so persistent? And why can't we make our models just better? So that's sort of, to start things out, I sort of want to mention that, we haven't solved the problem. But maybe sort of more fundamentally, I think that there are a few directions that I would sort of recommend for the field as a whole, which maybe tie in better to the topics of this workshop, which I think are more about trustworthiness and robustness from a very, very much broader perspective than the very limited perspective that I'm kind of addressing technically here. So what my wish list for the field would be is something like the following. I think there needs to be a better understanding about the key motivations behind why we're looking at this robustness problem. So I think a lot of people, and this actually came out of discussions I had from talking about people at this workshop, because I think oftentimes it's the implication seems to be that this is the biggest problem with deep learning systems. So deep learning systems work everywhere. They work great. They're secure, except for this problem of LP norm attacks. And and this is hopefully, as you can tell right now from this talk, this is completely untrue. And I hope that we can get a better understanding of these key motivations, which in my opinion are much less about actual security and more about the fundamental nature of deep learning, of the classifiers we learn and their sort of what they can do, their smoothness, and these kinds of properties about them. But having said that, I think we also need a much better understanding. So second and third parts are related here. We also need a much better understanding of where robustness of any type can sizably impact the practical security of machine learning, and where this interface will be between robustness, as I've framed it here, sort of as this min-max problem, where it's a very game theoretic formulation, it's a very sort of mathematical formulation and narrow formulation. Where can this narrow formulation sort of play with our practical understanding of what we want in a robust classifier? And finally, if I would say one last thing, I think it might be also a really good idea to move beyond the standard image, sound, video, etc. domains that deep learning has been so successful in so far. There are a lot of domains that are much, say, lower dimensional, where robustness is really important. Robustness and safety and verification are all very important. Things like control and other domains, where, by the way, there's a huge history of robust control. But there are a lot of other interesting domains that I think we could consider that go beyond the kind of classical deep learning setups, where these approaches may find, in fact, even more application. Because when it comes down to it, you can never actually certify an image classifier, right? You can't give a spec for what all pedestrians in a road look like. And so thinking about other domains could be very valuable here. All right, well, with that being said, thank you very much. I'm looking forward to the panel in a few hours. The papers and code are going to be available on my website. And I also want to thank my students as well as some of my external collaborators here. And it's great to thank everyone for attending this sort of virtual session, and hope to be able to answer some more questions at the panel.